Okay, so we all know the AI revolution is here, right? And it is incredibly hungry. We're talking about a demand for power and water that's starting to strain our planet's resources to the absolute limit. So, what if the solution isn't on Earth at all? What if we could just, launch our data centers into space? I know, it sounds like something straight out of a sci-fi movie, but some companies are actually trying to make this happen. So in this explainer, we're going to dig in and figure out, is this a total stroke of genius or just a really, really bad idea?
Right, let's dive into this. To really get why anyone would even consider such a wild idea, we first have to understand the sheer scale of the problem we're facing right here on the ground. The growth of AI, well, it's pushing our infrastructure to the brink, creating a very real crisis.
And honestly, this quote just nails it. Data centers are these hidden engines powering our entire digital world, but they have this voracious, almost parasitic appetite for our planet's most important resources, energy and water. To give you a sense of what we're talking about here, a big nuclear power plant generates about 1 gigawatt of power. So by 2030, data centers in the US alone could need the output of 130 nuclear power plants. That is an absolutely staggering amount of energy. Now, what's really fascinating is the huge difference between the old and the new. A conventional data center for something like cloud storage, it might use as much power as a small town. But an AI hyperscale data center, these are the gigantic facilities built specifically for AI. We're talking about the power equivalent of a major city. In some cases, more electricity than every single home in an entire state combined. The jump is just massive. And it's not just about electricity. Cooling these server farms takes an incredible amount of water. One report described the effect on a local area as being like a giant soda straw sucking water out of that basin. And a lot of this water is just lost to evaporation, meaning it's gone. It never even goes back into the local ecosystem. So, faced with this growing crisis of land, power, and water, some people are looking up for an answer. The idea is as radical as it is ambitious. Let's just move the whole problem off planet. Let's put the data centers into orbit. And on paper, the idea is super compelling. Just imagine it. A facility in orbit with constant 24/7 sunlight, a totally reliable source of solar power. You'd have what sounds like a perfect infinite heat sink in the cold vacuum of space. And by moving these huge industrial buildings off-world, you could free up critical land and precious water back here on Earth. It's sold as the ultimate sustainable solution. But how well does this futuristic dream really hold up against the cold, hard realities of physics and engineering? All right, let's bring this idea crashing back down to Earth with a serious reality check. A former NASA engineer, someone who also worked at Google's AI division, laid out this amazing critique, breaking the whole problem down into 4 inconvenient truths that really challenge the core of this entire concept. So the first myth we gotta bust is this idea of easy, abundant power. Yeah, sunlight in space is more consistent, but grabbing it at the scale you'd need for a data center is a monumental engineering challenge. It's not somehow magically free or better than on the ground. And this is where the sheer scale of the problem really hits you. The solar array on the International Space Station, it's huge. It covers more than half an American football field. And yet, it only generates about 200 kilowatts. A single rack of modern AI GPUs can burn through 70 kilowatts. So just to power a tiny data center, you would need a solar array that completely dwarfs anything we have ever built or even designed for space. Okay, this is probably the biggest and maybe the most dangerous assumption. Everyone thinks space is cold, so cooling must be easy. But the physics of how heat actually works in a vacuum, it's completely the opposite of what you'd think. The expectation is that you have this giant, infinite fridge. The reality? It's a perfect thermos. See, because space is a vacuum, it's an amazing insulator. There's no air, no water to carry heat away through convection, which is how pretty much all cooling systems work here on Earth. So instead, the heat just gets trapped. So here's the crucial point. The only way to get rid of heat in a vacuum is to radiate it away as infrared light. And this process is way, way less efficient than convection. It requires gigantic surfaces, basically radiators, to work at all. Okay, let's go back to that 200 kilowatts of power from our giant solar array. To get rid of all the heat generated by that power, you would need a radiator system with a surface area of over 500 square meters. Get this, that is more than double the size of the solar array you needed to generate the power in the first place. And that's just to cool 3 server racks. 3! The scale is just mind-boggling.
Right, so even if you could somehow solve the power and cooling problems, you've got another relentless enemy to deal with: radiation. You have to think of space as a constant storm of tiny, high-energy particles just slamming into your computer chips. When they hit a sensitive spot, they can randomly flip a 1 to a 0 in your data. This corrupts your calculations, causes crashes, and silently messes up information. And over time, this constant bombardment physically degrades the chips, making them slower and less reliable.
And finally, how do you even get the data to and from this thing? Here on Earth, data centers are connected by fiber optic cables running at hundreds of gigabits per second with basically instantaneous response times. In space, you're stuck with radio or laser links, which are just so much slower. And if you put the data center far enough away to get that constant sunlight, like in a geosynchronous orbit, the speed of light itself means you have a half-second delay on every single round trip. That kind of latency would absolutely kill performance for most applications. And we haven't even touched on maintenance yet. Data centers are built with the rock-solid assumption that things will constantly break. Hard drives fail, power supplies die, network switches go down. On Earth, a technician just walks in and swaps out the part. In space, a single failed component could be a mission-ending disaster. You can't just make a service call to low Earth orbit. So given all these challenges, they seem pretty much insurmountable from a physics and economic standpoint, it really begs the question, why is anyone even talking about this? If the basic engineering just doesn't add up, what could possibly be the motivation? Well, if you look at discussions online and among experts, a few potential reasons come up that go beyond pure science. Some people think it's just a story, a narrative designed to attract investors, and maybe distract from the very real environmental issues we have with data centers on Earth. Others wonder if it's about trying to operate sensitive data processing outside of any country's laws and regulations. Of course, there's also the potential for military or intelligence uses where money is no object. Or maybe it's just pure, unfiltered techno-optimism, a belief that any problem can be solved if you just build a big enough rocket. So after this whole reality check, what's the real takeaway here? What does this all tell us about the future of computing and our relationship with our own planet? And that really leaves us with the final and, I think, crucial question. It's so easy to get excited by the idea of conquering a new frontier. But maybe the real innovation, the actual moonshot challenge, isn't about escaping our problems by launching them into orbit. Maybe the real challenge is having the cleverness and the will to solve them right here by completely rethinking how we build and power our digital world on the only planet we've got.